Hello, so in this video I'm going to talk you through a really important idea in statistics, which is hypothesis testing. Now, I'm not going to talk too much about what hypothesis testing is now. I'm going to jump in with a motivational example, and then hopefully you'll get the idea as we go along. So effectively, I have a coin here, okay? Now, I know that because the vast majority of coins which are in circulation have been made to very rigorous standards by the Royal Mint in the UK, I know that in all likelihood that this coin is probably going to be fair. In other words, there's obviously two faces, there's the heads and then there's the tails. If the coin is fair, it means that if I flip it, there is an equal chance of it landing on heads as there is of it landing on the tails, okay? So there's a half chance of being heads, half chance of being tails. But I want to test this, okay? So the way which I'm going to test this is quite simply taking this coin and just flipping it a number of times and seeing what it lands on. I'm going to basically obtain some sample data, and then I'm going to say, what's the probability of obtaining this sample data if that coin genuinely is fair? And then I can make my decision from there. So here we go. I basically start off by having a couple of different hypotheses. Now notice the spelling. Hypotheses, which is up here, is a plural. It means more than one. If I'm just looking at one, and you can see the spelling here, it's a hypothesis, okay? So I have two different hypotheses. The null hypothesis is the current belief, the thing that I currently believe. So at the moment, because I know that the vast majority of coins in circulation are fair, because they're made to very high standards, then I know that in all likelihood, just my null hypothesis, in all likelihood is that this coin is fair. In other words, if I flip it, there'll be an equal chance of it landing on heads as there will of landing on tails. Now the notation which I'm going to give to the null hypothesis, the current belief, is H0, okay? So H0 is going to be my null hypothesis. So H for hypothesis, and then the naught is the original belief, okay? Now, my original belief, my null hypothesis, is the coin is fair, okay? That's what I currently believe. In other words, the probability of obtaining a heads from this particular coin, so I'm going to look at the perspective of obtaining heads, is equal to 50%. It's half chance, okay? Whereas the alternative hypothesis, which I'm going to give H1 as the notation for alternative hypothesis, sometimes you'll see this called HA, but I'm going to call it H1 to be consistent with H0, is that the coin is not fair. In other words, it is biased. So it's more likely to land on heads than it is tails, or more likely to land on tails than it is heads. In other words, it's not equal chance of landing on each face. So therefore, the probability of obtaining a heads is not going to be equal to 50%. It's either more than 50% or less than 50%, okay? So these are my two hypotheses, and whenever you do this kind of hypothesis testing, you always come up with your current belief, your null hypothesis, and then you say, okay, what's my alternative hypothesis? What am I going to test this null hypothesis against, okay? Okay, so let's go through this then. So I've put my null and my alternative hypothesis at the top, and I'm just simply going to flip this coin a number of times. So I'm going to flip it once, and it's a heads, okay? Well, I know that if that null hypothesis is true, if this coin is genuinely fair, the probability of getting a heads from just flipping it once is 50%. So that's the probability of obtaining my sample. But I want to be a bit more accurate, so I'm going to obtain a bigger sample now. So I'm just going to flip the coin again, and lo and behold, it's a heads. Now, I know that if this coin is fair, if that null hypothesis is true, the probability of obtaining this sample, in other words, two heads in a row from two flips, is 25%. You happy? It's just a half times a half, okay? If that null hypothesis is genuinely true. In other words, the probability of obtaining a heads is genuinely 50%. But again, I want to build this sample up because this is not unlikely, like there's a 25% chance of this happening. So I'm going to build my sample up by flipping the coin again. So if I flip the coin again, and lo and behold, it's another heads. Well, now I know that the probability of obtaining three heads in a row, in other words, the probability of getting this sample, is about 12.5%, about 13%. Okay, so that's a little bit lower, so my alarm bells are starting to ring here and thinking, is this coin actually fair? Because the probability of getting three heads in a row is actually only about 13%. But nonetheless, I'm going to keep going. So if I flip the coin again, and I get another heads. Well, now I know that the probability of obtaining this sample, four heads in a row, is about 6%. So I'm going to keep going because probability is getting lower. Like the more heads I get in this sample, the probability of getting this sample now is getting lower and lower and lower if that null hypothesis is actually true, if the coin is genuinely fair. But I'm going to keep going. I'm going to flip it again. I get another heads. All right, well, the probability of getting five heads in a row is about 3%. And if I go one more time, the probability of getting, 6 heads in a row is 1.6%. And I can keep going again and again. So 7 heads in a row is 0.8%. And 8 heads in a row is 0.4%. So what I've done here is I've started off by saying, look, I assume that this null hypothesis is true. I assume that this coin is fair. In other words, the probability of obtaining a heads should be 50%. Then I flip it a number of times and I obtain a sample. And it just so happens that my particular sample, which I've just done, is 8 heads in a row. And I say, well, okay, what's the probability of actually obtaining 8 heads in a row if my null hypothesis is true, if that coin is genuinely fair? Well, I find that it's just basically a half, or 50%, to the power of 8, which comes back as about 0.4%. So hopefully alarm bells are starting to ring here, because you're like, well, look, it's not unlikely. It's not impossible for you to get 8 heads in a row if that coin is fair. But you know, and you've got your kind of mathematical and your sort of intuition hat on, you're probably sitting there thinking, but it's pretty unlikely, right? You're more likely in 8 flips to get a mixture of heads and tails, right? So it doesn't necessarily mean that that coin is not fair, but you're more likely to be inclined that that coin is biased. In other words, the probability of getting a heads is not equal to 50%, just based on this sample data. So what have we got going on here then? So we make our decision, okay? And we said, well, look, we started off by saying, look, we have the null hypothesis, which is this coin is made fair. In other words, there's an equal chance of getting a heads as there is tails. Probability of getting a heads is 50%. The alternative hypothesis, the coin is not fair, it's biased. In other words, the probability of getting a heads is not equal to 50%. Then I flip this coin 8 times. And when I flip this coin 8 times, every single outcome in my sample, every single flip, resulted in a heads. And I asked the question, well, okay, what's the probability of that happening? What's the probability of getting 8 heads in a sample of 8 flips if that coin is fair? And it comes back as 0.4%. So I now am tasked with making a decision. Is this coin fair or isn't it? Okay. So what's really important here is to say that if the coin is fair, the probability of getting 8 heads in a row, in other words, the probability of getting this sample, which we've just done, is 0.4%. So some really important terminology which I want to introduce here. The 0.4% is something called a p-value, the p standing for probability. Just remember the p-value, it's really important you understand this, the p-value is the probability of obtaining this sample, 8 heads in a row, if the null hypothesis is true. In other words, if this coin is genuinely fair. Okay, so the probability of getting 8 heads in a row if the coin is fair is 0.4%. The 0.4% is what I'm going to base my decision on over whether the coin is actually fair or not. And you can kind of look at this and say, well, look, is it likely or is it unlikely that the coin is fair? In other words, is that p-value, is the probability of obtaining this sample if the null hypothesis is true, is it high or is it low? Well, first of all, I need to come in here and I need to ask the question, well, what do I mean by high? What do I mean by low? I need to define that, okay? So, what do we mean by p-value is high or low? Well, I'm basically saying if the coin is fair, the probability of getting 8 heads in a row is 0.4%, the 0.4% being the p-value. I need to decide what is high and what is low, okay? So, what I'm going to basically do here is I'm going to introduce a cutoff level. I'm going to basically say that any p-value which is less than this significance level, this cutoff point, is going to be constituting a low p-value. Anything above this cutoff point is constituting a high p-value. So I basically predefine, I say, look, this is the limit. This is the point where I start to say, something doesn't sound quite right here. This p-value is too low. In other words, the probability of obtaining this sample, if that null hypothesis is true, if this coin is genuinely fair, is too low. And we call that cutoff point the significance level, which we often give the notation alpha, okay? So, if the p-value is low, then the sample data shows that the null hypothesis is unlikely to be true. In other words, if that p-value occurs below our cutoff point, below our significance level, then that means that the sample data shows there's evidence which shows that the null hypothesis is unlikely to be true. However, so we say that that's basically the sample which we've just collected is significant, okay? In other words, we can reject that null hypothesis. We're saying, look, there's enough evidence here because we have a low p-value. That p-value, the probability of obtaining that sample, if the null hypothesis is true, is low enough to say, well, actually, something sounds quite fishy here. It's probably the case that that null hypothesis, in other words, the coin being fair, is not true. So we reject the null hypothesis, okay? Now just be really careful here, because this does not mean that that null hypothesis is definitely not true. Like, it could be true. We've just shown that p-value of 0.4%. We've just shown that if that null hypothesis is true, the probability of obtaining our sample is 0.4%. Okay? It's just with hypothesis testing, we kind of say, well, look, based on this p-value, we get quite a low p-value. So therefore, we're starting to suspect something's not quite right here. And the only thing which can't be right has got to be that hypothesis that we came up to start off with. Like our sample data, as long as we're collecting that sample data correctly and we've taken appropriate measures there, we know that's correct. Okay, so it doesn't necessarily mean that the null hypothesis is definitely not true. We're just saying that based on this particular sample data, it suggests that the null hypothesis probably isn't correct. Okay, so we say the sample is significant. Now this is really important as well. It means that when you're talking about statistics, you can only ever use the word significant in this context. In other words, you've gone away, you've taken sample data, and you've said, my p-value is less than my significance level, okay? That's what significant means in statistics. So if you're ever writing a report up or ever writing anything down in statistics and you use the word significant, it means you've done a hypothesis test, it means you've obtained the p-value, and you've said my p-value, the probability of obtaining this sample, assuming the null hypothesis is true, is less than whatever my significance level is. That's what significant means in statistics, okay? It doesn't mean anything else. So if you use the word significant in statistics, you have to use it in this context and no other context is allowed, okay? So I need to be really clear here as well. We've rejected the null hypothesis. In other words, we've got a p-value which is so low. The probability of obtaining 8 heads in a row, if that coin is genuinely fair, is so low. That p-value is less than our significance level, less than our cutoff point. We've rejected the null hypothesis. In other words, the coin is not fair, okay? But that does not necessarily mean that the alternative hypothesis is true. Now remember, the alternative hypothesis is that the coin is biased, okay? We're going to need to do some more tests in order to test the null hypothesis, the alternative hypothesis is true or not, okay? So this idea of testing, looking at p-values, is only testing the null hypothesis. It doesn't really tell you anything about the alternative hypothesis, okay? So that's really important. So, what about the significance level? Well, the significance level, remember the significance level is the cutoff point, the point where we say, yep, the p-value is low now, we're probably saying that the null hypothesis is not true, we're rejecting the null hypothesis. It can be whatever you like. However, there's a few things to bear in mind. If you use a large significance level, for example, 20%, 30%, 40%, so in other words, if you get a p-value less than 40%, you're going to reject that null hypothesis, you're probably not going to be that confident in your test, okay? Because actually more sample data will be rejected in that case, okay? Because you're more likely to reject the null hypothesis because more p-values will be classified as low, so you're not going to be as confident in your results, okay? Whereas if you use a really small significance level, for example, like 10, 5 or 1%, okay, then you can be more confident in your test, okay, because you're less likely to reject the null hypothesis because there are fewer p-values that will be classified as low, okay? In other words, your sample will be significant, okay? So when you're choosing a value for the significance level, it's important to be aware that choosing a too large a significance level will mean that you lose confidence in your test, but also if you use a smaller significance level, you're going to be more confident in your test, okay? So significance level is related to the thing which we're looking at in the last video, which is confidence levels, okay? So how it's related is that significance level is always 1 minus confidence level. So what that means, if you choose a significance level as 5%, it means that you can be 95% confident in your test, okay? And again, you can build a confidence level, and it means that you're basically building a really wide confidence interval. And of course, as we've sort of discussed in that last video, the wider the confidence interval, the more likely you are to attain the true population mean, okay? So just be aware, significance level is still related to the thing we were looking at in the last video, which is also to do with confidence intervals, okay? It's just 1 minus whatever the confidence level was to get the significance level, okay? So, just a reminder of the p-value, because a lot of people misinterpret this p-value, so I want to really make sure you understand what it's talking about. The p-value literally says, what is the probability of obtaining this particular sample data? So when I took my coin and I flipped it 8 times, okay, and I obtained 8 heads, what's the probability of obtaining that particular sample, or a more extreme sample, if the null hypothesis is true? okay? So if you're choosing a high p-value, it means that you failed to reject the null hypothesis. In other words, if you get like a 90% chance of obtaining this sample, if the coin is fair, if the null hypothesis is true, then actually you just failed to reject the null hypothesis. You're like, well, actually that null hypothesis seems fairly reasonable, okay? Whereas if you choose a low p-value, if you end up with a low p-value, in other words, there's a low probability of obtaining the sample data if the null hypothesis is actually true, you end up rejecting the null hypothesis, okay? In other words, you're starting to say that null hypothesis doesn't seem correct anymore based on this sample data that's in front of me, okay? So we never, ever say that we accept anything. So we never accept the null hypothesis and we never accept the alternative hypothesis, okay? Because this implies that we can find the true state, which we can't, okay? So we can never, ever obtain what the true state of this particular system is. We can never say, yep, that's true or that's true. We can only say, look, these are our claims and there's evidence to suggest that we can fail to reject the null hypothesis, or there's evidence to suggest that we can reject the null hypothesis. We never say that the null hypothesis is true, and we never say that the alternative hypothesis is true. So never, ever use the word accept, okay, when you're using hypothesis testing. Okay, and also we only ever refer to the null hypothesis, okay? We never talk about the alternative hypothesis. The alternative hypothesis is there to help us set up the test, okay? But we never ever in our conclusion refer to that alternative hypothesis, okay? We only ever refer to the null hypothesis because the test is set up assuming null hypothesis is true. So as a result, it doesn't tell us anything about the alternative hypothesis. If you like, you could go away and test the alternative hypothesis, your null hypothesis, okay? But because the whole test is set up around assuming that the null hypothesis is true and then asking what's the probability of obtaining this sample if the null hypothesis is true, we can't talk about the alternative hypothesis in our conclusion, okay? So just be aware of those two things. We never accept anything and we only ever refer to the null hypothesis in our conclusions, okay? All right, fine. So what's the testing process then? Number one, we establish what we currently believe to be true. That's our null hypothesis, okay? Then we get some evidence to support this. So in this case, I assumed that my coin was fair. That was my null hypothesis. Then I went out and I actually flipped this coin a number of times, in this case 8 times, and I got some sample data, some evidence to support that null hypothesis, okay? So that's my sample data there. Then I asked the question, well, okay, if that null hypothesis is actually true, how likely is it that I will obtain this sample data? Okay, so how likely is it that our current belief is actually to be true? And that's how we obtain the p-value. If that null hypothesis is true, what's the probability of obtaining this sample? If that p-value is high, then it means that we failed to reject that null hypothesis. In other words, we haven't got any reason to say that that null hypothesis is not true. However, if that p-value is low, in other words, the probability of obtaining this particular sample data is really low if that null hypothesis is true, then we're basically saying, yeah, we can reject that null hypothesis. That null hypothesis probably isn't correct, okay, based on this sample data. So then we ask, do we have the reason to change our current belief? So therefore we look at the case, well look, do we have a low p-value or is our sample significant? They're pretty much the same thing. So if you have a low p-value, it means your sample is significant. Remember, we've talked about what significant means in the context of statistics, okay? Now, notice that the p-value does not directly tell us the actual state of the null hypothesis. In other words, whether it's true or false, okay? It's more like a tool. And it's a tool which tells us the strength of evidence against the null hypothesis being true. Okay, so in other words, the p-value doesn't actually tell you whether the null hypothesis is true or not. It basically just says, look, this is the strength of evidence. This is the probability, the p-value. This is the probability of obtaining this sample if that null hypothesis is true. Okay, so it's, if you like, the strength of evidence against the null hypothesis being true. So basically, here I've got my null hypothesis and alternative hypothesis set up here. I've got my sample data, which in this case, 8 heads in a row when I flip this coin, and I found the probability of getting that sample, assuming that the null hypothesis is true, is 0.4%. I just simply ask the question, well, okay, how ridiculous does that null hypothesis seem now? Okay, so a p-value of 0.4 implies that we should attain sample data like ours 0.4% of the time if the null hypothesis is true. So let me just clarify what that means. If I flipped my coin, so if I did 1,000 rounds of flipping the coin 8 times, okay, I obtained 1,000 samples just like ours, flip the coin 8 times, do it 1,000 times, okay. 4 of those rounds, 0.4%, 4 of those rounds should result in every single flip being a head, okay. So then you can start to say, okay, can I use this evidence to decide whether we should update our initial belief, our null hypothesis, by relying on our senses of probability? Okay, so just remember that if I get a really, really small p-value, something like 0.01%, that does not mean that it's impossible that the null hypothesis is true. It doesn't mean that it's impossible to obtain this sample data, okay, if the null hypothesis is true. It's only very unlikely, okay? So the statisticians, if you like, only work with the evidence that's in front of them. So p-value of 0.01% means exactly that. It means that 0.01% of all of the samples that you obtain should result in a sample like this, or more extreme, okay? So just be aware that it doesn't mean it's impossible, okay? It doesn't mean it's impossible to obtain this sample. It just shows that it's very, very unlikely. So statisticians are kind of using their intuition of probability and using it in relation to the significance level, where that p-value is high or low, to obtain the result of our test, okay? So, the conclusion of our test will be wrong some of the times, okay? So we'll come on to this in just a second. It's all about testing errors, which is really important when you're doing hypothesis testing, okay? But before we do that, I actually want to come to this question here. I want to show you how you should actually go about calculating this particular test and how we should do a hypothesis test. So we have here a question, and it says that a particular type of fuse is claimed to break at 3 amps. So you're all aware with a fuse in an electrical circuit, basically current runs around an electrical circuit, and the idea is if there's too much current, if the current gets too hot, there's too much current running around the circuit, then obviously components can start to fail. So as a result, you introduce a fuse, which is a specific component, usually a very cheap bit of, I don't know, silicon I think it is, that is designed to break at a particular current. So if it goes beyond, if the current of the circuit exceeds a particular level, that particular component, the fuse, will break, and then basically the rest of the circuit is broken, and then it protects all the other components, which are much more expensive to replace, okay? So we've got a particular type of fuse that is claimed to break at 3 amps. Now, previous evidence supports the manufacturer's claim that the standard deviation of this particular type of fuse is 0.1 amps. And we want to basically see whether this claim up here is correct, okay? So if you like, this is our null hypothesis. A particular type of fuse is claimed to break at 3 amps. That's our null hypothesis, okay? So basically we go out, we collect a sample data. So we go out, collect 60 types of fuse, and we collect those, and we measure the mean current that the fuses break at. So in other words, we stick an amp meter in the circuit, and we basically measure the amp, which is the amperage which is running through the circuit, the amount of current that's running through the circuit, and we basically see at which point each of these fuses break at, okay? And we basically find that the average current that the fuses break at from these 60 types of fuse, so when we do our 60 sample size of 60, we find it's 3.2 amps, okay? So is there evidence from this particular sample of 60 types of fuse that the manufacturer's claim that the fuses break at 3 amps is correct at the 5% level of significance? Now this is really important. When we're talking about our level of significance, remember that's the cutoff point. That's the point where we say, look, anything above 5%, any p-value above 5%, so in other words, when we obtain this particular sample, we measure this particular sample, if this sample comes back as high, if the probability of obtaining this sample, given that the null hypothesis is true, in other words, the fuses do genuinely break at 3 amps, if the probability of obtaining this particular sample is more than 5%, like 10%, 12%, 13%, 70%, anything more than 5%, we're saying, look, there's not enough evidence to reject the null hypothesis. In other words, we fail to reject that null hypothesis. However, if we come back, the probability of obtaining this sample is less than 5%, if the null hypothesis is true, then we can reject that null hypothesis. So let's actually go through and calculate this. Now I'm going to write it down in a little bit more systematic way so that we can kind of keep track of what's happening here. I'm always going to start off by defining what my null hypothesis is and what my alternative hypothesis is. So I'm going to write down H0 and H1. Well, in this case, I've got that H0 is that the current should, or the fuse should break when the current of the circuit reaches 3 amps, okay? So I should basically say that H0, okay, is basically that the mean breaking point, so the mean, should be 3 amps or more, okay? So I'm just going to put mean equals 3, okay? On the basis that if the current has to go above that, so it has to come from below to above that. So I'm just going to say if it reaches 3 amps, then that's fine, okay? H1, what's the alternative hypothesis? Well, I need to look in my sample, okay? So I'm basically needing to test whether it actually breaks at 3 amps or not, okay? So I'm basically going to test, well, okay, does it break when it's not equal to 3 amps? So that's what I'm supposing. I'm basically assuming, first of all, that the mean breaking point of these fuses is when the current of the circuit reaches 3 amps. That's my null hypothesis. That's what the manufacturer claims is true. My alternative hypothesis is that it doesn't break at 3 amps. It could be more than 3 amps, it could be less than 3 amps, okay? So in other words, the way which I'm going to interpret not equal to is that the mean could be more than 3 amps or the mean could be less than 3 amps, okay? Now this is really important, okay, because I'm assuming that these things follow a normal distribution. In other words, the point which the fuses break at follow a normal distribution, okay? Which means that when I draw my normal distribution of where these currents or where these fuses break at, in the middle, I should have 3 amps. That's my current supposed hypothesis. That's what I currently believe to be true. And remember, throughout the whole testing process, I assume that null hypothesis is true, okay? And then I'm basically told that, look, previous evidence supports the manufacturer's claim that the standard deviation is 0.1 amps, okay? So basically, if I look at 3 standard deviations each side of the mean, I end up with a distribution that looks something like this. So 2.9, 2.8, and 2.7. So what my job is to do now is to basically look at this and say, okay, I want to test at the 5% level of significance, which means that 5% of the time, 5% of all of the probability outcomes that occur underneath this curve, so all the outcomes, should result in rejecting that null hypothesis, if the null hypothesis is true, remember, okay? So if I'm looking at 5% level of significance, I'll write that down, so alpha, which I'm going to call my level of significance, is 5%. I'm basically saying that I need to test 2 things. I need to test it being more than 3, and I need to test it being less than 3, but I only want to look at 5% of my sample data in total. So what that basically means, if I just get rid of my standard deviations each tide, okay, what that basically means is if it's more than, I'm going to be looking at a region on the graph which is up here, okay, and if it's less than, I'm going to be looking at a region on the graph down here. So because it's not equal to, in other words, because it's both greater than and less than, we call this a two-tailed test, because I'm literally looking at the 2 extremes in my sample. Okay, I'm looking at the 2 extremes in my sample, the 2 tails, if you like. Now, I know that put together, I need to reject the null hypothesis 5% of the time. That's what the 5% level of significance means. It means that 5% of the time, I end up rejecting the null hypothesis, even if the null hypothesis is completely true, which remember is what I'm assuming. Okay? Which means that these 2 shaded red regions on my graph, so this region here and this region here, should add up to 5%. But because there's 2 tails, I'm going to split them equally. That's the fairest way, which means that this tail up here should be 2.5%. And this tail down here should contain 2.5% of my data as well, okay? So now what my job is to find the cutoff values. In other words, how many standard deviations each side of the mean will I cut off, okay? So in that region, okay, you see these 2 regions here, we call those the critical region. So the critical region are any measures of standard deviation from the mean, from the hypothesized mean, when we reject the null hypothesis. So the critical regions, okay, are the values in which we reject the null hypothesis, okay? So these are the values in which we reject the null hypothesis being true, okay? In other words, they're any values that occur to the left of this point or to the right of this point. These are my critical regions, okay? The cutoff points, so the points where those regions start, are called the critical values. I'm just going to go CV for short. They're critical values, okay? So I need to first of all find where those critical values are. Well, remember these are in measures of units of standard deviation. So in the middle, I've got my hypothesized mean, okay? That's my mu, that's my hypothesized mean. In this case, my hypothesized mean is 3 amps, okay? So I need to work out, well, okay, how many standard deviations each side of the mean do I need to look in order to include 2.5% of my data in my 2 tails? Okay, so let's have a look at that. Okay, so first of all, I need to figure out what type of test am I using. So is it going to be a Z test? Is it going to be a T test? All right. So I asked the same questions I was asking in my confidence intervals. Number 1, have I got a sample size greater than or equal to 30? If the answer to that question is no, I know straight away that I can use a T test. The other question I ask, if that answer to that question is yes, is do I know the population standard deviation? Okay, again, if the answer to that question is no, I have to use a t-test. Otherwise, if the answer to both those questions is yes, I can use a z-test. So in other words, I have two options here. If I ask these two questions, so n being greater than or equal to 30, and do I know my sigma, do I know my population standard deviation? If both of those questions are answered yes, I can use my z-test. If either of those questions are answered no, I have to use my t-test. So let's check it out. Let's see what evidence we've been given. So look, I've basically been told, look, previous evidence supports the manufacturer's claim, so this line here, previous evidence supports the manufacturer's claim that the standard deviation is 0.1. That is my population standard deviation, okay? That's my population standard deviation because I'm not obtaining it from the sample data that I've collected. In other words, the sample of 60 fuses, okay? So in other words, I do know the population standard deviation. Now I look at my sample size. Well, look, my sample size in this case is 60 because I collect 60 different types of the fuses. So now I can come down here. Do I know that my sample size is greater than or equal to 30? Yes, I do. Do I know my population standard deviation? Yes, I do. It's 0.1. So therefore, in that case, I can jump in and use a z-test, okay? So I'm going to first of all look at this, okay? I need to find my critical values. I need to find how many standard deviations each side of the mean are my cutoff values. In other words, values more extreme than that, so either to the left or to the right of that, will mean that I reject that null hypothesis. So I'm going to bring up my z tables here. So I'm going to go paste. Well, look, I have three tables here. I have my Z tables on the left and my T tables on the right. Well, look, I don't want the T tables in this case, so I can get rid of that. So basically, I'm looking in these tables, and I'll just zoom in. I'm looking in these tables for 2.5%. So just remember, 2.5% is equal to 0.0250. Okay, so that's the value I'm looking for, because remember it's given as a decimal in my table. So I just go through these tables, I look in all here, I look for these numbers here, I'm looking for 0.0250, or as close to as I possibly can find it. Well, as it happens, that value is there. Okay, now if there's not that value which lies in there, because it's not always going to be 2.5%, it might be 5%, it might be 99% or 1%. If we can't find that exact value, find the value that is closest, okay? Rather than trying to interpolate it or something like that, just simply find the value that is closest. So in this case, I get 2.5% exactly. Well, that's going to occur, so I find the row first of all. So that's negative 1.9, okay? And then what column is it? So it's negative 1.96 is the lower value, and obviously by the symmetry of the curve, the upper critical value is going to be positive 1.96, okay? So in other words, my lower critical value is negative 1.96. So in other words, any standard deviations which lie below negative 1.96 will be rejected. And if I have a sample data that lies more than 1.96 standard deviations from the mean, that will also be rejected as well. Okay? So now I just need to work out, well, okay, given this particular sample data, so let's write down my sample data. I have n equals 60, so my sample data here. So here's my sample data, okay? I've been given that the sample size is 60. I've also been given the sample mean. So the sample mean in this case is 3.2. It's been given here. So my sample mean in this case is 3.2. Okay? So now I just need to use this to find my test statistic. Okay, so just remember, I'm first of all going to write down my distribution. So I know it's going to be normally distributed, but I'm going to use all 60 types of fuse put together to create a distribution. So I know that the mean of those 60 fuses is still going to be normally distributed. I've got my sample mean, which is 3.2, and I've also got my variance, because I can use my population variance is 0.1. So yeah, 0.1 is my standard deviation, so my variance is going to be 0.1 squared. Okay, except it's not, because I need to use the central limit theorem, so it's going to be 0.1 squared decreased by a factor of whatever my sample size is, because of course you understand as I take more things in my sample, that variance should decrease, and it decreases by a factor of n. Okay, cool, so now I'm in a position where I can actually calculate my test statistic. Now all my test statistic literally asks is how many standard deviations from the mean does my, from the hypothesized population mean, so in other words the 3 amps, okay, how many units of standard deviation does my sample data lie away from that hypothesized null hypothesis mean, okay? So I need to work this out. Well, just remember that the way which I can work this out, okay, is just simply by using the formula, okay, using the formula of standardizing. So I'm going to use x bar minus the true population mean divided by my standard error, okay. So in this case, my standard error is 0.1 over root of 60. So if I actually sit down and work this out, well, my x bar in this case is 3.2. My mean, well, my mean is my hypothesized mean, because remember, I'm assuming throughout the duration of this test that my hypothesized mean is correct, okay? My null hypothesis is correct. My null hypothesis says that the current should break at 3 amps, or the circuit should break at 3 amps, okay? I need to divide by my standard error, which is 0.1 over the root of 60. And I'll stick all of that in a calculator and see what we come out with. So I basically come back with something like 15.5, okay? So that there is my test statistic. That literally says that is how many units of standard deviation my sample data lies away from my hypothesized mean, okay? So my hypothesized mean says that the sample should break at 3 amps, okay? My sample data says, well, look, I've gone out, I've collected 60 types of these fuses, okay, and I've found that the average breaking point of these fuses is 3.2 amps. And I've said, well, look, that particular sample data lies about 15.5 standard deviations away from the hypothesized mean, okay? So therefore, when I come up here, because 15.5 lays way out over here, okay, so that's my test statistic. 15.5 lies well out over here. It's way beyond the 1.96 units of standard deviation where my cutoff value was, okay, my critical value was. So therefore, in that case, I reject the null hypothesis, okay, because if you notice, my critical region extends all the way down here as well. Okay, so my critical region extends all the way down here, and my critical region is basically the region in which I reject the null hypothesis, okay? So I'm basically only saying, look, any values between 1.96 units of standard deviation from the mean, those are the only values where I have a chance of failing to reject the null hypothesis. Well, in this case, I end up with sample data that lies 15.5 units of standard deviation from the hypothesized mean. That's way beyond the cutoff value, or the way beyond the critical value of 1.96 units of standard deviation from the hypothesized mean. Therefore, I reject the null hypothesis, okay? Now, just to be clear here, I want to also find the p-value. So the way in which I find the p-value is I come into my tables and I literally look for 15.5 units of standard deviation. Well, you can see that the highest units of standard deviation is 3.49, okay? So way beyond that, and that's basically, well, it's basically 0%, okay? So what I can basically say here, if I write my little conclusion, which you should always do when you do a hypothesis test in order to reach full marks, okay? So here's my conclusion, okay? I can say that since the test statistic of 15.5 lies beyond the critical value of 1.96. Remember, these are given in units of standard deviation from the hypothesized mean, okay? I can also say, so that's in terms of my test statistic, okay? I can also say that since my p-value, in other words, the probability of obtaining this particular sample data if the null hypothesis is true, in other words, if that null hypothesis is actually 3 amps, if that is actually correct, the probability of obtaining this particular sample of 60 types of fuses all breaking at a mean temperature of 3.2, or mean amperage at 3.2 amps, okay? The p-value, I'm not going to write is equal to 0% because it's not, okay? We saw from the table that there's actually no value there, and actually anything more than that is going to be pretty much 0%, okay? But it's not quite 0%. It's going to be 0.00000 like 1%, okay? It's going to eventually not be 0%, okay? So because the p-value is less than, and I'm going to say 0.01%. Okay, so that's what I'm going to write instead. Instead of it writing being equal to 0%, because it's not, okay, it's going to basically be less than 0.01%. It's going to be less than something really, really small, okay, which is less than the significance level. In other words, the significance level is kind of like our cutoff probability level, okay, the point where we decide that the p-value is low. Then we say that the significance level of 5% okay? Then we basically say, so then we reject the null hypothesis, okay? So we reject the null hypothesis that the fuses break at a mean current of 3 amps, okay? So notice the wording which I've done here. I've done 3 things. Number 1, I've done the test from the perspective of the test statistic. I said, look, our particular sample data lies 15.5 units of standard deviation from the hypothesized mean breaking point of those fuses of 3 amps, okay? Which is well beyond the cutoff value of 1.96. Remember, the 1.96 says, look, anything beyond 1.96 of unit standard deviation from the hypothesized mean is enough evidence to suggest that the null hypothesis probably isn't correct, okay? But I've also done it from the perspective of a p-value. So I've said, look, because the p-value is well below the 0.01%, okay, it's basically nearly 0%, like the probability of obtaining a sample that lies 15.5 units of standard deviation from that hypothesized sample mean of 3 amps is like well below 0.11%. It's more or less 0%, okay, but not quite. Okay, and it's certainly less than the significance level of 5%. Remember, significance level is the point where we say the p-value goes from high to low. Okay, then we reject the null hypothesis, but that's not enough. Okay, so I don't just say we reject the null hypothesis. Okay, I also try and put that conclusion in context. Okay, so in this case, I'm looking at whether the fuses break at 3 amps or not. That's my null hypothesis, and that's what I think is true with my null hypothesis. But actually, this sample data suggests that there's evidence to reject that null hypothesis, okay? In other words, the mean fuses probably don't break at 3 amps. Now, notice that I never say anything is definitely true. The wording is very, very particular here, okay? So you must always make sure, okay, so when you give your conclusion, you do it in these 3 stages. Number 1, you do it from the perspective of the test statistic. You say, where does your test statistic lie? Does it lie in the critical region or outside the critical region? Number 2, you then do it from the perspective of the p-value. You say, look, here is the p-value. This is the probability of obtaining this sample, okay? And then is it less than the significance level or not? Okay. Then the third thing is you actually say whether you accept or reject, sorry, not accept, fail to reject or reject the null hypothesis, okay? And then you always put it into context with the question, okay? So it's not enough just to say, hey, look, we reject the null hypothesis. You actually need to say what that means, okay? That's the job of a statistician. We talked about that in the first theme, the first video. It's all about how you interpret statistics, okay? So hopefully that makes sense. Okay, so let's have a look at another question then. So, the mean lifetime of a battery is found to be 70 hours. A sample of 15 batteries is collected to test this claim, and the batteries of this sample is measured to have a mean and standard deviation of 68 hours and 3 hours respectively. So we're asked to test at the 1% level of significance whether there is evidence to suggest that the mean lifetime of these batteries is actually less than 70 hours or not, okay? So the way in which we're going to set this question up is going to be slightly different, okay? First of all, I always advise you to write down what the null hypothesis is and what the alternative hypothesis is as well, okay? So in this case, let's read through it. The null hypothesis is that the mean lifetime of the batteries is 70 hours. Okay, so I'm going to write that down as the mean lifetime is equal to 70 hours. Now, the alternative hypothesis is actually given to us in that last statement. Okay, we need to test whether the mean lifetime of the batteries is actually less than 70 hours. So in other words, the alternative hypothesis is that the mean lifetime is less than 70 hours or not. Okay, so now we go through and let's actually write down what our sample data is. Okay. So the sample data, which we've been given. So this is, if you like, the evidence to suggest whether that null hypothesis is true or not, okay? So let's have a look. So I go out and I collect a sample of 15 batteries. That's our sample size, okay? So I write that down, so n equals 15. And I find that the mean and standard deviation is 68 hours. So 68 hours, that's the mean, with a standard deviation of 3 hours. That's what respectively means. So in other words, I give the mean first, then the standard deviation. So respectively means it comes in that order, okay? So the mean, in other words, the sample mean, x bar, is 68 hours. And the standard deviation, so I'm going to write that down as S for sample standard deviation, because remember, I'm measuring the standard deviation of the sample. I've not been given the standard deviation of the population, okay? That's found to have 3 hours, okay? So that there is my sample data, okay? That's the evidence which I'm going to use to suggest whether this null hypothesis is actually true or not, whether there's enough evidence to reject that null hypothesis, okay? So first of all, I'm going to figure out what type of test am I going to use. First of all, what type of tail am I going to look at in this test? Because of course I've got a normal distribution, which these batteries follow. Okay, so here's my normal distribution. I always encourage you to draw down this normal distribution. In the middle at the moment is our hypothesized mean lifetime of 70 hours. So I'm going to put mu equals 70 in the middle, okay? And I'm basically going to say, well, look, am I looking at a one-tailed or a two-tailed test? Well, in this case, I'm only interested in values which are less than 70, in which case I'm only looking at values which lie to the left of our hypothesized mean, okay? And obviously I'm going to allow some particular allowance, okay? So my cutoff value is actually going to lie somewhere down here. So my tail of my test is down here, okay? Now, how big is my tail? So in this case, I'm going to call it a left-tailed test, obviously because I'm looking at the left tail of the distribution. Obviously, if it's more than, I'll be looking at the values to the right of my hypothesized mean, in which case it'll be a right-tailed test, okay? But in this case, it's a less than, so it's a left-tailed test. I'm only interested in values that lie in this particular critical region here. And I need to test, I've found my significance level, at the 1% level of significance, okay? So that there, the alpha equals 1%, that there is my level of significance, okay? So anything less than 1% will be rejected. So any p-value which comes out as less than 1% will be rejecting the null hypothesis being true. And anything more than 1%, so p-value, probability of obtaining this sample more than 1%, will be that the hypothesis or the null hypothesis is there's not enough evidence to reject it, okay? So let's have a look at this. Let's first of all find our critical value. So where does this critical region start? So this region at the moment I know has got to contain 1% of my data. So my question is, well, okay, what is my critical value there? Okay. So in order to find that, I need to find out what type of test I'm using. Is it going to be a Z test or is it going to be a T test? So let's ask ourselves the questions then. So is n greater than or equal to 30? And do I know the population standard deviation or not? Okay. If the answer to both those questions is yes, I can use the Z test. If the answer to either of those questions is no, I can use the T test. All right, let's have a look at this. So, first of all, what's the sample size? Well, the sample size in this case is 15, okay? So the answer to the first question is no, so therefore I'm going to be using the t-test. But even if I did, if the answer to that question was yes, I still didn't know my population standard deviation anyway. My standard deviation is given in terms of my sample, which is 3. So I'm going to have to be using the t-tables. So if I bring in my tables down here, okay, I don't want my Z tables, which are the first two tables, I want my Z tables, okay? So in order to use my T tables, remember, I'm going to have to find my degrees of freedom. So in this case, my degrees of freedom, because it's just a one sample, is exactly the same as when we're doing confidence intervals. It was just n minus 1. So in this case, my n is 15, that's my sample size, take away 1. So my degrees of freedom is equal to 14. Okay, so let's have a look at this. So it's come down to my tables. We need to find 14 degrees of freedom. So in other words, I'm going to be looking in this row here, okay? And I need to find what my significance level now. My significance level is 1%. Now just be aware that my significance level is 1% because I'm looking at one tail, okay? If I was looking at two tails, it would be whatever the probability of that tail was, okay? So because I know that my significance level is 1%, which gives me my confidence level of 99%, I can basically come down here, okay, and I can basically look at the 1% level of significance. So 1% is this one here, so 0.01, okay, which gives me my 90, well, it's going to give me 98% because of course it'll be split over two tails if I wanted to. Okay, fine, so let's find the intersection points. So 14 and 0.01, let's find where these two things intersect. They intersect at 2.624. So that's how many units of standard deviation to the left of the hypothesized mean I'm going to start my critical values at. So 2.264. Okay, so any standard deviations which lie, sorry, if my sample here lies less than 2.264 units of standard deviation from my population mean or my hypothesized mean, then I know that I can reject the null hypothesis, okay? Sorry, that's 624, isn't it? So 2.624. So basically, if I find that this particular sample data that I've collected, if that lies less than 2.624 units of standard deviation from the hypothesized mean of 70, then I know there's enough evidence to reject the null hypothesis. So my next task is to actually find my test statistic. How far does this particular sample data lie from the hypothesized mean of 70? Okay. So in order to calculate my test statistic, I just use my standardizing formula. So my test statistic, in other words, how many units of standard deviation does my sample lie from the hypothesized mean? I can just simply use my test statistic. So that's going to be, well, let's have a look. It's going to be x bar minus mu over my standard error. Okay, so let's have a look at this. So x bar in this case is equal to 68. My hypothesized mean in this case is 70. That's what I'm assuming to be true. Okay. And I'm dividing by my standard error, which is going to be, well, it's going to be 3 divided by root of 15. So I haven't written down my distribution, but I think that's okay. So, okay, let's stick all of that into a calculator and see what we get. So we're going to get negative 2.58. So that's my test statistic. In other words, what I'm saying there is that my particular sample, which I've just been given here, my sample which I've collected, lies 2.58 units of standard deviation from the hypothesized mean, okay? Oh, just be careful up here when I calculate my critical value. That's negative, of course, because it's to the left of my hypothesized mean, okay? So where does 2.58 lie? Well, 2.58, this test statistic, lies about there, okay? So it's not in the critical region. So 2.58 lies there. It's not in the critical region. It's not in the region of rejection, if you like, okay? So in that case, I failed to reject the null hypothesis. So let me write down my conclusion down here. So I'm going to break it up. So my conclusion. Okay, so my conclusion, first of all, is that because my test statistic which was negative 2.58, lies to the right of my critical value, which was negative 2.624, okay, then basically I say that I failed to reject the null hypothesis. But remember, I also need to calculate that p-value to give me some extra support in my conclusion. So in order to calculate that p-value, I basically look in the t-tables at 14 degrees of freedom and try and find as close as possible to 2.58 units of standard deviation. Let's have a look, okay? So let's come down here. I'm going to look in this particular row because I'm still looking at 14 degrees of freedom. Let's have a look at this particular row here. I'm trying to find 2.58, or as close as possible to 2.58, okay? So 2.58 in this case lies somewhere between those two things. So in other words, I can say it lies about halfway between 0.01 and 0.02 as my p-value, so 1% and 2%. So I'm going to say my p-value is approximately 1.5% in that case, okay? So my p-value is approximately 1.5%, okay? Which is fine. So let's have a look at this then. So let's actually make the conclusion. So based on our test statistic, because the test statistic lies to the right of our critical value, then I can basically say that we fail to reject the null hypothesis. So because I failed to reject the null hypothesis, that basically implies that this particular situation of the lifetime of the batteries, okay, so there's evidence to suggest, so there is not enough evidence to suggest that the mean lifetime of my batteries is anything other than 70 hours. Okay, so remember, I'm wording it so that I'm not saying anything is true. I'm saying, well, look, there's not enough evidence to suggest that the mean lifetime is not 70 hours. Okay, so just be aware of that. Okay, so let's just finish off on one final little question then. So I'm going to stick with batteries, but this time I'm going to test battery lifetimes of two different types, okay? So I'm going to basically say, look, I've got battery A and I've got battery B. Okay? Now I know that battery A has a population standard deviation of, let's say, 3 hours. Okay, and battery B has a population standard deviation of 4 hours. Okay, so notice my notation, sigma 1 corresponds to battery A, sigma 2 corresponds to battery B. Okay, I basically say that sample size of battery A, so I go out and select 50 batteries of battery A, and I select 60 batteries of battery B. Okay, I find that the sample mean of these 50 batteries of battery A has a lifetime of 200 hours, and the sample mean of battery B, they have a lifetime of 203 hours, okay? In fact, I'm going to turn that to 201 hours, okay? So my job now is to test this, okay? Now, because I have two different batteries here, my null hypothesis in this case is going to basically say, well, look, is the true population of these batteries the same, okay? So in other words, if I go out and collect these two batteries, is the mean lifetime of these two batteries actually the same at the population level? Is the parameter the same, okay? The alternative hypothesis, well, okay, I'm going to say that the alternative hypothesis is that one battery is better than the other. So in other words, mu1 in this case is lying less than mu2, okay? Because that's certainly what the evidence is suggesting anyway, okay? So let's have a look at this, okay? Now, just be aware that if I look at this, I have that mu1 take away mu2 is equal to 0, okay? And if I also look at this, I'm basically saying that mu1 take away mu2 is greater than 0, okay? So just be aware that's another way of expressing my alternative and my null hypothesis, okay? Now, just be aware that because my alternative hypothesis is saying one is less than the other, okay, one is less than the other, so mu1 is lying less than mu2, what that literally means is when I draw my curve out, okay, let's suppose that, let's actually colour code this. Let's suppose that battery 1 I'm going to draw in red and battery 2 I'm going to draw in green. Okay, so what that basically means is with my null hypothesis, if I draw my curves out, because I have now two batteries, it means I should have two normal curves, okay? And what that basically means is that mu1, well look, it has a slightly smaller standard deviation than mu2, okay, than battery 2, okay? So basically when I draw the curves, I'm basically saying, well look, battery 1 should have a curve that looks something like this, and battery 2 should have a curve that looks something like this, okay? In other words, they're distributed, they're centered around the same mean value, okay? That's what my null hypothesis is saying, that the means of the two batteries should be the same, okay? However, the standard deviations are slightly different. So the standard deviation for battery 1 is slightly smaller than the standard deviation of battery 2, which means the red curve should be slightly less spread out than the green curve. Whereas if I look from my alternative hypothesis case, well in that case I'm saying that the mean of battery 1 should lie to the left of the mean of battery 2. So it means that when I draw my two curves out, what I'm literally looking at here is that this curve, the red curve, should actually lie to the left of the green curve, okay? Because that's literally what my alternative hypothesis is saying, okay? They're centered around different values. So really what I'm looking at here when I'm doing my two sample hypothesis test is I'm looking for the difference in the mean values, okay? I'm looking at the difference in the peaks of those curves. The null hypothesis says that the difference in those curves is equal to 0. The alternative hypothesis is saying that actually there is some particular difference in that curve, okay? There's some positive difference in that curve. Because of course I'm doing mu1 take away mu2, okay? Sorry, that should be less than 0, shouldn't it? If I rearrange that, okay? So that should be less than 0. In other words, when I take away mu1 from mu2, there should be a negative distance. In other words, mu1 lies to the left of mu2, okay? However, the principle is still the same. Because this is a less than, we'll look at from the perspective of mu1, this is going to be a left-tailed curve, okay? So it's going to be a left-tailed test. So in other words, I'm just going to draw out one curve and that curve will represent the differences, okay? So, okay, I've got my significance level. Well, my significance level, let's just suppose is 5% again, okay? So let's just put our significance level here at 5%, okay? If it's not given to you, 5% is a pretty good kind of choice of our significance level, okay? Now I actually need to work out what the distributions of these sample means is going to be, Okay, so if I do the distribution of mu1 take away mu2, so the distribution of battery 1 take away battery 2 of these two samples, okay? Well, they're still going to be normally distributed. By the central limit theorem, I know they should be mu1 take away mu2. We looked at this last week with our confidence intervals. The standard deviation, though, well, by a central limit theorem, should be sigma 1 squared over n1 plus sigma 2 squared over n2. That's how I combine together my two samples, and I gave you a proof of that in the last video, okay? Now I can go through and I can actually ask myself a question, well, what type of test am I going to use, t-test or z-test? So just remember, in order to use the z-test or the t-test, I need to ask myself the question, is n1 greater than or equal to 30, and is n2 greater than or equal to 30? So they both need to be greater than or equal to 30. If the answer to that question is no, I know straight off the bat that I should use a t-test, okay? If the answer to that question is yes, I then go on and ask myself the question, well, do I know the population standard deviation for battery 1 and the population standard deviation for battery 2? If the answer to that question is no, again, I'm going to use the t distribution. And if the answer to that question is yes, in other words, the answer to both those questions is yes, I ask myself the z distribution. Okay, so let's have a look at this. So is n greater than or equal to 30 for both? Well, n is greater than or equal to 30 for battery 1, and it's greater than or equal to 30 for battery 2. Okay, so that condition is satisfied. Next, do I know the population standard deviations for both? Well, yes, I do. They're given in the question. They're both standard deviations given in terms of the population. So in that case, that question is yes. Therefore, I can get away with using the z distribution. Okay. Just remember, if you did use the t distribution, the degrees of freedom for the t's distribution will be n1 plus n2 take away 2. It's basically just the sum of n1 minus 1, the degrees of freedom for distribution 1, plus the degrees of freedom for distribution 2. Okay. So that's basically the same. Okay, so in this case, we're going to use a z distribution. So I'll bring up my tables again. So I don't need to worry about the t distribution. I can get rid of those ones. And I'm basically going to look at my z distribution tables. Okay, fine. Well, first things first, I'm actually just going to draw myself out a curve. So here's my curve. And this curve is basically going to represent the differences because I'm looking at the differences in my two samples. So rather than kind of try and worry about these two curves, I'm basically just going to draw a new normal distribution, which is going to represent the differences in the lifetimes of these two batteries. Okay, so I'm supposing that the differences in the two batteries is 0 to start off with. That's my mu1 equals mu2. In other words, the difference is 0. Okay, and then basically I can look at the normal curve each side. So that's a terrible normal curve. Let me try to draw that again, something like that. Okay, there we go. Now I'm looking at a left-tailed test. So in other words, I'm basically saying, look, I'm looking for values that lie this many standard deviations from the hypothesized difference in the means or more, okay? So I know that because the significance level is 5%, that area there should also be 5%. So my next job is to find what the critical value is. In other words, how many standard deviations from the hypothesized difference in the means do I need to look at in order to reject my null hypothesis? So in other words, to contain 5% of my data. So if I look in my curves, okay, I'm going to be looking at, well, I'm going to be looking at 0.05, okay, so 0.05 or as close as possible. So 0.05 will lie halfway between those two things, okay. Now you could interpolate if you like, okay, in fact it lies halfway in the middle, so that's exactly what I'm going to do. So negative 1.6, let's say 1.645, okay, so negative 1.645, yeah, is going to be my cutoff value. So negative 1.645, that's my critical value. In other words, if I end up with my sample data lying to the left, okay, so more extreme than this, okay, then it means that I can reject that null hypothesis. So let's now go ahead and calculate our test statistic. In other words, let's figure out how many units of standard deviation does the difference in our particular sample lie, okay, so test statistic. Now just remember, in order to calculate the test statistic in this case, I'm looking for the test statistic for the difference in the mean. So it's going to be the difference in the sample means, take away the hypothesized difference in the population means, okay? And that's going to be all divided by, well, it's all going to be divided by the standard error, okay? So it's going to be divided by the standard error like so. Okay, so let's have a look at this. So the difference in this sample means, well, I can work that out because I've got the two sample means up here. So the difference in the two sample means, I've constructed it as x1 bar take away x2 bar. So make sure you construct your order in the same way. So it's going to be 200 take away 201. So that's going to be negative 1. Okay, so that's the difference in my sample means. So that's going to be negative 1. okay? Then I need to say, well, okay, what is the difference, or the hypothesized difference in my means? Well, are you happy that the hypothesized difference in my means, this thing up here, is just 0? Because I'm basically assuming that the mean lifetime of those two batteries is the same, okay? So I'm basically assuming those two things are 0. So if I zoom in again, I'm going to basically take away 0 here. Then if I divide by my standard error, well, I come up here to my distribution, and I'm basically just going to take the square root of that thing. So it's going to be the square root of, so sigma 1 squared, I've got it up here, that's going to be 3 squared, over n1, which is 50, plus sigma 2 squared, which is 4, over 60. Okay, so let's write that down. So it's going to be 3 squared over 50, plus 4 squared over 60. And I'm going to stick all of that into a calculator to see what we get, okay? So I get negative 1.49 or negative 1.50 to 2 decimal places. So that's my test statistic. That's how many units of standard deviation my actual sample differences in the means lie, okay? So negative 1.50 lies here, okay? So negative 1.50 lies here. Okay, which means that I failed to reject the null hypothesis because it doesn't lie in the critical region. Okay, I'm also going to calculate my p-value. So in other words, what probability is associated with negative 1.50 units of standard deviation from the mean? So again, I can look in my tables. I can find negative 1.50. So here is negative 1.5, and I'm going to be looking at negative 1.50, which is that first column. So if I find the intersect, I find it's 0.0668. Okay, so that's my p-value. So my p-value, which is associated with negative 1.5 units of standard deviation from the hypothesized difference in my means, that was my 0. Let me write it out again, 0.0668, which is 6.68%. Okay, now that's above my my level of significance of 5%. So again, that's another reason why I reject the null hypothesis. So let's write down my conclusion then. So it's very simple. Number one, I write down my test statistic. So my test statistic, okay, which was negative 1.50. My critical value was negative 1.645. So in other words, anything below negative 1.645 units of standard deviation from the hypothesized difference in the means, I would reject. Anything above that is acceptable. Okay, so negative 1.5 lies above the critical value. So I'll just write crit value for short for the sake of time. Which was negative 1.645. I'm also going to do it from the perspective of the p-value here as well. Okay, so I get the p-value, which was 6.68%, is above my cutoff value, my significance level, of 5%. Okay, so what's the conclusion of my test? I failed to reject the null hypothesis. So what that basically means is that there is not enough evidence to suggest a difference in the mean lifetimes. Okay. So that's it. It's as simple as that, okay? I'm just going to quickly write down a recipe for how you should work with this, okay? So number one, when you're doing hypothesis testing, what's the first step you should always write down? Well, the first step is that you should always write down what your whole hypothesis is. So in other words, what your null hypothesis is and what your alternative hypothesis is. That's the first thing that you should always write down, okay? Second step is that you should establish the type of test, okay? So establish the type of test. So that means, first of all, are you doing a one-tailed or a two-tailed test? So left or right-tailed? Or are you doing a two-tailed test? Okay, in other words, both less than or equal to. Remember, you work that out from the alternative hypothesis. So basically, if H1 is that mu1 is equal to mu2, that means it's a two-tailed test. If mu1 was, sorry, not equal to mu2, that was basically a two-tailed test, okay? If mu1 was greater than mu2, that would be a right-tailed test. And if mu1 was less than mu2, that would be a two-tailed test. And of course, you can adapt that according to what type of test you're doing. So if it's just one sample, of course, you won't have a mu2, you just have a particular value instead, but it's the same principle, okay? But you also need to establish whether it's a T or a Z distribution, which you're going to be using, okay? And again, you establish that just by asking the question, have you got big enough sample size? Is it greater than or equal to 30? And also you establish that through your through whether you know your population standard deviation or not, okay? The next thing you need to do is you need to work out your critical values, okay? So I'll write down critical value and then S in short, because it depends whether you're doing a two-tailed test, a right-tailed test, or a left-tailed test, okay? Remember, you do that according to, well, okay, you work out your level of significance, okay? So if it's a 5% level of significance, you work out how much data you need to include in those two tails, okay? Then from that, you work out your test statistic. In other words, where does your sample data lie from the hypothesized mean or the hypothesis, okay? So you work out your null hypothesis and you work out where your test statistic lies in relation to your null hypothesis, okay? You then go ahead and you work out your p-value, okay? And then step 6, you can come up with your conclusion. Now remember, your conclusion is nice and easy, okay? So first of all, you relate your test statistic to your critical values, okay? So you relate your test statistic to your critical values, okay? So does it lie to the left or right of the critical values? Does it lie in the critical region, or does it lie outside the critical region? Number 2, you relate your p-value to your significance level. In other words, does your p-value become less than your significance level? So in other words, are you going to reject the null hypothesis, or is it greater than your significance level? Are you going to accept, or are you going to fail to reject the null hypothesis? And then part C, you state the conclusion, okay? So in other words, do you reject or fail to reject? And you also put your conclusion in context with the question. So if you're talking about lifetimes of batteries, you need to say what rejecting the null hypothesis means in the context of these lifetime of batteries. If you're talking about marks of people on a test, you need to talk about why rejecting the null hypothesis is relevant in the context of the marks on the test. So how should somebody go forward? Okay, if you're talking about weights of chocolate bars, if you fail to reject the null hypothesis, what does that mean for the weights of the chocolate bars? Okay, so always make sure you put it in context for you. Okay, be a statistician there. Okay, but that's it. Okay, that is it with regards to hypothesis testing. It's a 6-step process. Okay, now again, it's just practice, and there's loads of practice which you can do. Okay, if you wanted to stop the video here, that is fine. That covers everything that we need to cover in this course, okay, for hypothesis testing. However, I have just got a few extra slides, which if you're interested, you're more than welcome to go through, which talks about the types of errors which you can make when you're doing hypothesis testing. So just be aware, this is everything that is covered in the course, but I have just got a few little bonus things, which if you wanted to carry on and watch the video, you're more than welcome to do so. Okay, so great. So if you're watching the video now, it means you've chosen to carry on with the video, which is absolutely fantastic, okay? I want to come back to this slide here, which is all about the errors which we can make, okay? And I really want to draw your attention to this bottom box here, which says that, look, just because we have a small p-value, so something like 0.01% or even less than that, as we did in one of our examples, it doesn't mean that it's impossible to obtain that particular sample if the null hypothesis is true, okay? So the null hypothesis could still be true, even though there's a really low likelihood of obtaining this particular sample data that we've got, okay? So the statisticians can really only work with the evidence that's in front of them. So I'm going to talk through then the different types of errors that we can make when we're doing our hypothesis test, and then from that we can actually make more informed decisions. So the conclusions of our test will be wrong some of the time, okay? It's not a perfect kind of foolproof method, okay? So in other words, we can incorrectly reject or fail to reject the null hypothesis. Now, if that happens, if the result of our test is incorrect, then we call that an error, okay? Now, you notice that we only ever look at it from the perspective of the null hypothesis, and we only ever say that we reject the null hypothesis or fail to reject the null hypothesis. So therefore, because those are the only two things that we can do incorrectly, I guess, there are two types of errors that we can make. And very imaginatively, we call those two types of errors a type 1 and a type 2 error, okay? So basically I use this little sort of table here to remind myself of what the type 1 and type 2 error is. So let me talk you through it. The first situation we can have, so the decision is, if you like, the row, okay? So we can either reject the null hypothesis or fail to reject the null hypothesis. This is the result of our test, okay? But if you're aware, like, it's got to be a truth. Either the null hypothesis is true or the null hypothesis is not true, okay? That's the kind of actual truth. That's the actual thing that is happening, okay? We can only work on the evidence that's going in front of them, so we can either reject the null hypothesis or fail to reject the null hypothesis. But remember that the null hypothesis could be true or it could be false, okay? That's what we don't know at the moment. That's what we're trying to test, okay? So in other words, if we reject the null hypothesis, and if the null hypothesis is actually false, that's a correct outcome, okay? So the two things in green are actually correct. So we reject the null hypothesis was actually false. That's a great outcome, that's correct, okay? Or we can fail to reject the null hypothesis and the null hypothesis is actually true. That's also a correct outcome as well. So there's two correct outcomes on this particular slide here, okay? However, there are also the two errors. So let's suppose, first of all, we reject the null hypothesis. So with my coin example, my null hypothesis was that that coin was fair, okay? Well, if I reject the null hypothesis, if I say, nope, that coin is there's not enough evidence to suggest that coin is fair when I got those 8 heads in a row, I'm saying that p-value is well below my level of significance, therefore I reject the null hypothesis. But what if my null hypothesis was actually true? What if this coin was actually fair? Well, in that case, I've rejected something that was actually true, okay? So I call that a type 1 error, okay? I say that coin is not false, that coin is not fair, when actually it is. That's a type 1 error, okay? The other error I can make is if I fail to reject that null hypothesis. If I say, well, look, there's not enough evidence to suggest that that coin is not fair, when actually that coin is biased, that coin is not fair at all. We call that a type 2 error, okay? So just be aware. A type 1 error is if we say this null hypothesis is false, but actually that null hypothesis is true. A type 2 error is saying, no, there's not enough evidence to suggest that that null hypothesis is false, when actually it is false, okay? So we fail to reject the null hypothesis when actually the null hypothesis is false. That's a type 2 error, okay? So let's actually work it through then. So let's look at the perspective of the type 1 error first of all. So in other words, we say that this coin is false, this coin is not fair, when actually it is fair, okay? So that's a type 1 error, okay? So if we have a look at this, the probability of obtaining a type 1 error is the same as our significance level. Now you might want to just pause the video here and just think, well, why is it? Why is it our significance level? Well, just remember that the reason being is because the significance level is basically saying 5% of your data should be rejected. If you look at our tails, okay, if we look at our curves, okay, we're basically saying, well, look, if our values lie on the left-hand side, if we lie in the extreme kind of portion of our curve, or if we lie on the right-hand side, if we lie in the extreme kind of left and right-hand side, we're basically saying that that area is according to alpha. That's according to our significance level. That's how much of the data we are going to reject just naturally, okay? So that is going to basically be the cause of a type 1 error. So in other words, we're saying we lie in that critical region when actually that null hypothesis is true. Okay, so in that case, that size of that region is according to alpha, our significance level. So therefore, we're saying that we have a type 1 error there. So it's just equal to whatever our significance level is. Okay, so I've given a quick example there just to sort of illustrate that. So I say if our significance level is 5%, then that means that 5 in every 100 samples will result in a low p-value anyway, because that's what 5% of that's what significance level of 5% means. It basically means reject 5% of your data. Okay, and therefore we reject null hypothesis just by pure chance, even though the null hypothesis is actually going to be true. Okay. So note that the probability of obtaining a type 1 error increases as the number of tests increase, right? Because 5% means that 5% of the time you should reject the null hypothesis, even though the null hypothesis should actually be true, okay? So obviously, if I increase the number of things that I'm taking, if I do the number of tests, increase the number of tests, then therefore 5% will be 5% of all of the tests which I'm going to do. Okay, that's what 5% of the rejection means. So if I'm rejecting 5% of the time, okay? So therefore, if 5%, then 5%, there you go. Therefore, we need to do what's known as a post-hoc correction. Now, there's lots of them out there. Bonferroni, Benjamini, Hochberg. These are all kind of standard correction tests which are out there, and there's different ways in which you can do them. But they basically adjust your p-values to control for them being a type 1 error. Okay, because I've just said that a type 1 error should happen 5% of the time. In other words, we reject the null hypothesis when actually it's completely true. Okay, it should happen 5% of the time. So what these post-hoc corrections do basically is adjust that p-value to make it less likely to be a type 1 error, okay? So, what about a type 2 error? Well, type 2 error is when we fail to reject the null hypothesis, but null hypothesis is actually false, okay? So in the case of our coin example, I'm basically saying, nope, this coin is completely fair, when actually it's not fair, okay? That's a type 2 error. So the probability of obtaining a type 2 error is given the notation beta, and it's just simply given and it's going to be affected by our sample size and the choice of our significance level. Now, by the way, the probability of working out a type 2 error, it's much more complicated than just finding out the probability of type 1 error. Probability of type 1 error, nice and easy, just whatever our significance level is, because that's how much of the data we are going to reject just naturally anyway, okay? But probability of type 2 error is controlled by, it's affected by our sample size and also by the choice of our significance level. So sometimes the probability of type 2 error can be a little bit more awkward to work out than the type 1 error, okay? So if I use a large sample size, for example, the probability of a type 2 error will decrease, okay? So the bigger the sample size, the lower the value of beta, the lower the value of the probability of a type 2 error. But of course, with a larger sample size, that also means that the probability of a type 1 error increases. So again, you know, that's something to kind of bear in mind. Just be aware it's also hard to directly calculate the probability of a type 2 error in relation to a type 1 error, because we also need to base it on how strict our criteria is for rejecting the null hypothesis, okay? So for example, if you make that criteria more strict, then obviously the probability of a type 2 error will decrease. However, the probability of a type 1 error will also increase. So again, it's this kind of playoff. Type 2 error versus type 1 error. You know, yes, okay, you can reduce the probability of getting a type 2 error, but as a result, that's probably going to mean that you're going to increase the chance of getting a type 1 error, okay? So type 2 error can't be estimated directly, but it can be estimated as a function of the true population effect, okay? So I'm not going to go into how you calculate probability of a type 2 error because it's a little bit more awkward, but if you are interested, there's loads of videos out there kind of talking you through that anyway, okay? So I'm going to now ask you the question, what's worse, type 1 error or type 2 error? So just a reminder, type 1 error is basically saying that we reject the null hypothesis when actually it's completely true. In other words, we say, no, this coin is not fair when actually it is, okay? Type 2 error is saying, no, this coin is completely fair when actually it's not, okay? So we fail to reject the null hypothesis when actually it's false. So I'm going to just alter the context of my example slightly. And I'm going to look at a machine which is manufacturing medicine. Perhaps it's manufacturing particular doses of a medicine which people have to administer themselves, okay? The dosage of this medicine should be 100 milliliters, all right? So the null hypothesis is saying that this particular machine is manufacturing medicine which is coming out at 100 milliliter dosages, okay? But of course, the alternative hypothesis is saying that it's not manufacturing 100 milliliter dosages, okay? So now I'm going to ask yourself the question, you might want to pause the video again and just think, what situation is worse? A type 1 error, in other words, saying that the machine is not manufacturing 100 milliliter doses, in other words, we reject the null hypothesis when actually it is, okay? The alternative error is the type 2 error, which is saying that we fail to reject the null hypothesis. In other words, we're saying that the machine is manufacturing 100 milliliter doses. That's what my evidence shows. Yeah, it's all good, okay, when actually it's not. That's a type 2 error, okay? So type 1 error, just to put that into words, is saying that you say that the machine is not manufacturing the correct dosage when actually it is, whereas a type 2 error is saying that the machine is manufacturing the correct dosage when actually it isn't. Now, what's worse, okay? Well, I think a type 2 is worse, okay? In this particular example, manufacturing medicine, it's imperative that each person gets the correct dosage, because if they get the incorrect dosage, then that may mean that they can end up dying. Like if they end up with a dosage which is like 1,000 millimeters, like 10 times the dosage which they're supposed to get, that can end up killing them. Okay, so obviously it's imperative that the patient gets exactly the right dosage, okay? So if you say that the machine is not manufacturing the correct dosage when actually it is, the worst that happens is that you halt the production process, you reset the parameters of the machine, and then you go again. So it's just basically just wasting time, but in fact, there's no kind of wastage there. All that happens, there might just be a little bit of wasted time and perhaps a few wasted medicine, okay? But it means that everybody's still getting the correct dosage. Whereas a type 2 error would be saying, yeah, the machine is all good, when actually it's not, when actually it's manufacturing the incorrect dosage. Okay, because that means that you're not picking up that the machine is doing something wrong, which means that potentially patients could receive the incorrect dosage because you didn't pick up on it. Okay, so actually a type 2 error is always worse than a type 1 error. So in fact, when I come back to that last slide, when I was saying, look, you need to control for the fact you could have a probability of type 2 error, probability of type 1 error, you can decrease the probability of a type 2 error, but then it will increase the probability of type 1 error. That's always preferable rather than trying to optimize the probability of a type 1 error and then sacrifice the kind of, you get a higher probability of a type 2 error, okay? So always, always, always try and reduce the probability of getting a type 2 error, even if that means the probability of type 1 error goes up, okay? I don't care too much about probability of type 1 errors. I care much more about probability of type 2 errors, okay? So I'm just going to quickly talk about the power of a test, okay? Because the power of a test is basically when you correctly reject the null hypothesis when actually it's untrue, okay? So in other words, it's just basically the probability of not making a type 2 error, okay? Not making a type 2 error. So in order to work out working out power, it's just 1 minus whatever the probability of a type 2 error is. So just be aware of these kind of terms out there. Again, I've not really gone into too much detail on the errors and things, okay? I could have drawn my curve and I basically say, look, here's 2 samples, here's a difference in my curve, that's the probability of a type 2 error, and the overlap is a type 1 error, and etc. and things like that. I've not gone into that. If you are interested in that, there's loads of resources out there, but I thought it made sense whilst we're talking about hypothesis testing just to put this little bit of additional appendices on the end, just tag that on there, just to make you aware there are some extra stuff to be aware of with hypothesis testing. But the important thing is that the probability of type 1 error, type 2 error, power of a test, you don't need to know about in this course. I've just given it in there because I think in case you're interested, in case you want to find out more about it.